In classical mechanics, today we are going to start a new chapter which is very important. Actually, in this chapter, we are going to discuss canonical transformations. And regarding these canonical transformations in this first lecture, I will just give you an overview of canonical transformations. And after this introductory lecture, we will see the detailed theory of these canonical transformations. In fact, you know that dynamical problems can be solved in more than one coordinate system. In fact, any coordinate system, there are a minimum number of independent variables or coordinates to describe the system, as you know. So, in a particular problem, it is possible that one of the coordinate system is more convenient than other, and that's why we transform a coordinate system from one coordinate system to another. For example, if you consider motion of a particle in a central force field, then you know, since motion under a central force field is motion in a plane, so in this condition people may either use Cartesian coordinate system or the plane polar coordinate system. But the use of the plane polar coordinate system while discussing the motion under central force field is actually more convenient. What's the reason? The reason is that if you will discuss the problem of central force field in Cartesian coordinate system, then there will be two independent variables, that is x and y. But if you will use the plane polar coordinate system, then actually there will be only one independent variable, only r, not theta, because in this case theta is a cyclic coordinate the coordinates will be r and theta, but theta is cyclic, so it does not appear explicitly in the expression of Hamiltonian. So it becomes easier to discuss the motion of a particle in central force field when we discuss its motion in the plane polar coordinates. So this is followed while discussing the motion of the particle in central force field, and this is the reason that we transform the coordinates from one coordinate system to another. In fact, broadly speaking, we can say there are two types of transformations. In classical mechanics, whenever you talk about the transformation, then we simply say that in broad sense you can say that there are two types of transformations. The first one is known as point transformation. Point transformation. Actually, when you say point transformation, this is simply a transformation of configuration space. And transformation of configuration space means what? This is only a transformation of position coordinates, not the momentum coordinates. So, if there will be a transformation of position coordinate from one coordinate system to another, then that is called a point transformation. So, if you consider that this qk are the position coordinates of the old coordinate system, and this capital Qk are the position coordinates in the new coordinate system, then transformation between Qk and small qk and capital Qk means what? If you know the values of this small qk, that is the position coordinate in the old coordinate system, then it is possible to find the values of this capital Qk by using the transformation equation. And the converse is also true, that if you know the values of this capital Qk, then it is possible to find the value of these small qk. So in general, symbolically we represent these transformations like this: qk, capital Qk is equal to capital Qk of small qkt, where t is actually time, and in the same way this qk may be expressed as a function of this capital Qk and t. So in short, you can say that in point transformation there will be a transformation of only position coordinates from the old coordinate system to new, or from the new coordinate system to old. But our primary aim in this chapter is to deal with the another transformation, which is known as canonical transformation. This is actually the core concept of this chapter. So first of all, as I have told you earlier, that in this lecture we will see only a very short account, a very brief introduction of this canonical transformation. When you say canonical transformation, which is also known as contact transformation, that means actually the transformation of phase space. As you have seen, point transformation means transformation of configuration space, but canonical transformation means transformation of phase space. But you know, in phase space, the state of a particle or a system is specified or stated in terms of two coordinates, the position coordinates qk and the momentum coordinates pk. You know, because in phase space this momentum coordinate is placed on the same footing as the momentum coordinates are placed on the same footing as the position coordinates. So in phase space these pk are treated as independent coordinate, just like qk. So if there will be a transformation of position coordinate qk and the momentum coordinate pk, but in such a way that the form of Hamilton's canonical equations of motion does not change, it remains invariant, or you can say that the form of these equations remain preserved, then such a transformation is known as canonical transformation or contact transformation. It means when you will change the small qk and small pk into the new coordinate system, the transformation should be in such a way that the form of Hamilton's canonical equation of motion in the new coordinate system must be in the same form as it was in the old system. So let us consider mathematically these things here. We consider that the let qk and pk. What are these? As you know, these are actually the position and momentum coordinates in the old coordinate system. Position and momentum coordinates in old coordinate system. And this capital Qk and capital Pk, let us consider these are position and momentum coordinates in the new coordinate system. New coordinate system. Let us consider. Then in fact these two sets of coordinates, that is the position coordinate and the momentum coordinates, are related by the transformation equation like this. You can express this transformation in this way, that this qk is equal to qk of q1, q2, so on qn and P1, P2, so on Pn T. And similarly, this Pk may be written as Pk of Q1, Q2, so on Qn, P1, comma P2, comma so on, comma Pn, comma T. And say this is your equation 1. In fact, in brief, you can write these equations in one by using the proper subscript. You can write it. So in brief, equations in 1 are written as, how you can write it. This Qk is equal to Qk, Qk comma Pk comma T, and Pk equal to Pk of a small qk, a small pk, and T. Say this is your equation 2. In fact, here k is equal to 1, 2, 3, so on up to n. Actually, the transformations defined in this equation 1 or this equation 2 both are same. These transformations will be called actually the canonical transformation, but only when the form of the Hamilton's canonical equations of motion in this new coordinate system will remain invariant. It means the form will remain same as that it was in the old coordinate system. Only then you can say that this transformation defined in equation 1 or 2 is actually the canonical transformation. So you can say that transformation defined in 1 and 2 is canonical if qk dot equal to del h prime by del pk and pk dot equal to minus del h prime by del qk. Can you say what are these equations? Actually, here I have assumed that this h prime is the Hamiltonian in the new coordinate system. So h prime equal to Hamiltonian in the new coordinate system. So let's see, what does canonical transformation means? Now you can easily understand it. Just I have written a transformation equation in equation 1 or in equation 2, both are same. Actually, we have assumed that small qk and small pk are the position and momentum coordinate in the old coordinate system, and capital Qk and capital Pk are the position and momentum coordinates in new coordinate system. Then you can express this position coordinate capital Qk as a function of the position coordinate and momentum coordinate and time of the old coordinate system. Time remains same, and similarly the momentum coordinate of the new coordinate system can be expressed as a function of the position and momentum coordinate of the old coordinate system. And this transformation defined in equation 2 or in 1 will be called a canonical transformation, but only when the form of the Hamilton's equation of motion does not change in this new coordinate system. As you know, Hamilton's canonical equation you have already studied. This is Qk dot equal to del h by del Pk and Pk dot equal to minus del h prime, del h by del Qk. So if you consider that h prime is actually the Hamiltonian in the new coordinate system, then if these two equations will hold, that is capital Qk dot is equal to del h prime by del Pk and capital Pk dot equal to minus del h prime by del Qk. If these equations hold, it means the form of the Hamilton's canonical equation of motion do not change. If these equations hold, it means form of the Hamilton's equations do not change, then you can say that the transformation defined in equation 1 or 2 is canonical transformation. Only then you can say it. Now, as the Hamiltonian is different in the new coordinate system from the old coordinate system, so you can also say that the Lagrangian of the system will be also different from the old Lagrangian. So in this condition, if L prime equal to new Lagrangian, then you can say that this L prime is equal to L. As you know that Lagrangian is a function of position coordinate, generalized velocity and time. So in this new coordinate system, the position coordinates are denoted by this capital Qk, generalized velocity will be capital Qk dot and time is t. Now the Hamiltonian of our system in the old and new coordinate system you can define, because you already know the definition of the Hamiltonian. So you can say if H be the Hamiltonian in the old coordinate system, then you know that this H is defined like this: H equal to summation over K Pk Qk dot minus L. You know it. And so in the light of this equation, if the transformation is canonical, then the new Hamiltonian in the new coordinate system, that is H prime, will be defined like this. This is summation over K capital Pk capital Qk dot minus L prime. You can see we have assumed that this L prime is the new Lagrangian. So in fact here this capital Qk and capital Pk are therefore referred as canonical coordinates. You can say that this capital Qk and capital Pk are what? These are referred as canonical coordinates. Canonical coordinates. In fact, the Hamiltonian in the Hamiltonian formulation, as we have already seen in the previous lectures, that the independent variables similar to generalized coordinates are actually the momentum. It means momentum is placed on the same footing as the generalized coordinates are placed. But the canonical transformation include the simultaneous transformation of independent position coordinate and the momentum and the momenta, you can say. It means this small qk and small pk are actually changed to the capital qk and capital pk in the canonical transformation. But this transformation will be called canonical only when you have seen the form of the Hamilton's canonical equation of motion does not change. Then you say that such a transformation is canonical transformation. Actually, this is just a brief idea of canonical transformation. In fact, in the next lecture, we will see what is actually the condition for canonical transformation, or how this transformation can be carried. Actually, for carrying this transformation, we need an idea of generating function of this transformation. So the subject matter of the forthcoming lecture will be the generating function for the canonical transformation.